Hello everyone. Thank you for viewing this talk. My name is Dalskov. I'm a cryptographic engineer at Partisia. I do cryptography. I do software engineering. This talk was originally given at our hackathon in December, like late November last year, and this is like a recording of that talk. Okay. The title of the talk is called The Right Amount of MPC, and let's just get right into it, what that actually means, what I'm actually going to talk about. So I'm going to talk about certain aspects of the MPC security model, or CK computation security model, namely privacy and input independence. And I don't want to talk about how these aspects are realized in the actual software that is running, but rather what they are on like a more intuitive level. And the reason I want to do that is that I hope that understanding these two properties allows you to understand what you can actually do with MPC in a way that allows you to use just the right amount of MPC. Because MPC is it's a very neat technology, but it's also a very expensive technology. So you don't want to overuse it, as it were. You want to use just the right amount so you accomplish whatever it is you wish to accomplish. And I believe in order to do that, you need to actually understand what the particular properties MPC or CK computation provides you in terms of security. Okay. To learn about MPC, you can do as you do with a lot of other things you want to learn about, and that is to go on Wikipedia, search it there, and then try to read the article that somebody else wrote about it. If you do this for MPC, you get a very dense, as in there's a lot of text, article about MPC or secure multi-party computation or privacy-preserving computation, as it says here. We can take out all the, I won't say uninteresting parts, but at least for understanding what MPC is, what it gives you, and so on, there is a lot of like noise in this text. And by removing that, we end up with two sentences here that I highlighted. Well, highlighted by removing the other text. The first sentence says that MPC is methods for parties to jointly compute a function over their inputs while keeping those inputs private. And secondly, that MPC is some cryptography that allows participants in this model, when they compute this function, to keep their inputs private from each other, or the cryptography provides privacy essentially. Okay, so summarizing here, MPC, it computes some function on some inputs. These inputs are private. And secondly, MPC is not really magic, it's cryptography. But for the purpose of this talk, I don't want to get bogged down in like the nitty-gritty details of like the math that is involved here, or like the software that is running it. So I will actually treat it as magic. But just know that there is some cryptography. Obviously, it's not just a pie in the sky. MPC is actually doable. It's doable by a lot of fancy cryptography that people have been spending a lot of time developing. Okay. For this talk, I'm going to use essentially this model, which is, well, at a high level at least, it's very close to what is, or it is essentially what is running on Partisia blockchain. So we have here on the right, we're going to have a blockchain that is a blockchain in all the usual sense of the words, meaning it's everybody can see what goes on here. Like everybody can see what's written here, everybody can talk with it if they want to, they can send messages through smart contracts, and all writes, so that is all the data that is on the blockchain is totally ordered, meaning that if this transaction 0, say, appears on the blockchain and then later transaction 1, it can never be the case that at some point it looks like transaction 1 came before transaction 0. Next to the blockchain, we have a MPC cluster. Concretely, this is run by 4 servers that talk to each other in such a way that if you view if you look at the communication between these servers, if you can somehow tap into the channels they have with each other, you cannot see what's going on there. That means that there is some sort of encryption going on. There's some authentication going on, so they know that they're talking to the right ones. In order to actually do the MPC, which is like an interactive protocol, they're sending some messages that uses a lot of fancy cryptography. But the key part here is that there is like a blockchain where everybody can see what's going on, and there's an MPC cluster which can do something for us. But treating this MPC cluster in this very concrete sense with 4 servers that talk to each other and so on, sort of forces me to also talk about how they do this talking to each other, what the protocol is and so on. And that's not really what I want to do, because it takes away from what they provide you, like what service they provide you, what properties they provide you. So instead, and in this talk, I'm going to treat this MPC cluster as simply like a black box. I call it the MPC box. The reason for doing so is that if we replace this now with like this magic black box, which is not exactly obvious why this should exist, but let's just assume it does for a moment, then obviously it's very private, right? There's nothing that allows you to see what's going on inside this black box, well, because it's black and cannot see what's going on. It's opaque. So therefore, at least intuitively, it must be private. But I must of course say here that there is a lot of cryptography going on here, and actually this cryptography allows us in a very formal way to treat MPC, to treat these 4 servers as a black box we cannot look into. So we can actually prove, like mathematically, that we can take these 4 servers, replace them with a black box that has some very interesting but very simple properties that I'm going to come back to like in just a minute. But the important part here is that this black box abstraction is a lot simpler, because we don't have to talk about what is actually going on inside there, what these 4 servers are doing, or however many servers we're using. Okay, so this black box, in a bit more concretely, it computes a function, and it computes this on some inputs. So we can imagine that people can talk with this box by sending some private inputs. You have A here in this model. A inputs a value 0, B inputs a value, value 0, inputs a value X, B inputs a value Y, C inputs a value Z. Inputs it into this box that has some function encoded in it. Maybe this function was the input of some other party. And then the output of this box, when it has received enough inputs, or all the inputs, or whatever the computation it specifies is supposed to do, it will produce an output which is running this function on the inputs. And it bears mentioning, of course, that this function can actually in principle be anything. There's very few limitations on what you can actually do with MPC in terms of what you can compute. That doesn't mean that you should put anything into this, because MPC is very expensive. In terms of the computation you have to do to actually execute an MPC protocol that computes some function. So while it is possible to, I don't know, encode Doom into an MPC computation, it's probably not a good idea, because it's going to be incredibly expensive, and it's not really obvious if that's like a good idea, basically. If you take this black box analogy, abstraction, if you will, and look at like the privacy guarantees it gives us, then it's fairly obvious what it actually provides. In particular, we can see that this box actually reveals nothing except what we can infer from inputs and outputs. That means that if we take the view of, say, A and B, say A and B decide to collude, so they share, B goes to A and says, oh, I inputted this value, or A goes to B and says, I input this value. And they do this in order to try to learn what C inputted. Then all they will be able to learn now is what they can compute by taking their own inputs, taking the output, and then trying to see what they can infer from this. Similar thing, of course, happens, or like applies to C. It will only be able to learn about the inputs of A or B, or both, what it can infer by inputting, by taking its own value. It knows this function was the one that was computed, it knows it gave this output, and then trying to see what it can infer from this. So this is a very simple privacy guarantee, and it has obviously, and as we'll see, some obvious restrictions. Namely, it's now more or less entirely dependent on what function you compute. If we compute the identity function, for example, then we're not learning anything essentially. If we're computing a sum, then we may or may not learn something depending on how many terms this sum has. And it becomes more and more complicated, of course, with more complicated functions. But the important part here is that privacy in MPC is essentially this. Nothing is revealed except what you can learn from inputs and outputs. Okay, so that takes care of like the first property I want to talk about. So let's look at this input independence property, which is the same one. And in order to like motivate this this property, let's imagine that A, instead of inputting some value X that it picked before, like this value X, it now has a special button where it's allowed to say, I want to input the same value as this other person. So it says, in this concrete example, it says, I want to input the same value as the party C. It's important to note here that this saying, I want to input the same as party C, contains no information about what party C actually inputted. It's just saying I want to do the same as this person without actually knowing what that thing was. And this is important because it shows that input independence is not the same as privacy. It's a distinct, separate feature, if you will, of MPC or property that we would like to have. Or I guess put differently, we can have a MPC computation that is private, perfectly private, that still allows people to input the same as other parties. If we do that, of course, so now we have something that is private, but it's not input independent, there's a lot of applications that become kind of hard to see why they would be interesting to compute an MPC. An obvious example would, for example, be an auction. If I am allowed in a secure auction, I cannot see anybody else's bid, but I'm allowed to say, oh, I want to bid the same +1 as this other person, or I want to bid the same exact thing as this other person, or in a vote, for example, say I want to vote the same as this other person, then that doesn't seem very very useful. So input independence is definitely a feature that we would like, but it's important to know that it's like a feature that is independent, or a property that is independent of privacy. Okay. So the rest of the talk, I really just want to talk about, well, 2 example applications of MPC, and I chose these 2 applications randomly, and so that they just so happen to illustrate both privacy and input independence in very nice ways. The first application I want to talk about, or I want to illustrate example, is an average salary. And I think everybody can guess what this computation is going to do. It's a very simple computation. People input what they earn. The computation computes an average. We do this inside MPC because nobody wants to announce to the whole world, or at least to their coworkers, exactly what they own, but they still want to get an idea of what people earn in this company on average. So this illustrates very nicely what MPC is, or sorry, what privacy is. But it also actually can be used to illustrate sort of, not exactly tricks, but places where you can look for optimizations and how you can look for these optimizations. So put differently, it also illustrates what the right amount of MPC could be in this particular computation. The second example I want to go through is front-run safe swaps. So it's a swap in the normal sense, just like a swap, like a Uniswap or something like this, where I can put in an order saying I have this many tokens, I want to swap them for that many tokens, and if that's possible to do, then this swap is executed and I pay that whatever tokens I specified and receive in return the other amount of tokens. Swaps on blockchains have this issue that people often frown upon, that it's possible to front run them. So if there is a certain amount of slippage between the actual price and the price that you specify in the swap, you can sort of abuse that to essentially earn money without risking anything. It turns out that you can actually use MPC to fix this issue. And the reason you could do that is because MPC is input independent. Or I guess if you want to be very technical about it, it means that if you have an input independent MPC computation, then you can use that computation to avoid allowing front running, or you can prevent front running on the swaps you place through this MPC. Another example, another thing that is illustrated by this example is that MPC can be useful even for very simple computations. And I'm going to, of course, come back to what this very simple computation is. Okay, so let's take the average salary example first. As I mentioned, the function is very simple. We compute a sum of the inputs and we divide by the number of inputs. So in this example, we have A who inputs the salary 42, B inputs salary 21, C inputs salary 33. The computation that this MPC box does is that it just takes the sum of the inputs, divides it by 3, and then it outputs this. So it will read these inputs that come from the different parties. They're, of course, private, so people can see that they put something on chain, they just can't see what that something is. It does this computation and outputs 32, which is pretty sure that's the right average here. And if we look at what the privacy like the privacy guarantee here, we can take the view of C. We see that this computation makes sense in the sense that C actually learns nothing about what A and B input here, right? Because what C can do is that it knows of course its own value. It knows that it has salary 33. It knows the output, the average salary, so to speak, is 32. It can multiply the average salary sort of to undo the division at the end of the computation, and then it can subtract its own salary. And what it gets, what it is left here is the sum of the other two people's salaries. But of course this could be anything, right? It doesn't learn exactly what B's salary is or what A's salary is, and all it knows is that the sum of these two people's salaries have to be this particular value. But there's many ways you can like satisfy this sum, and in particular that means that C actually doesn't learn anything about what the actual salaries are of these two people. On the other hand, if we take this view of, if we assume that A and B collude, so they will share internally or like privately between them their salaries, then we can sort of do the same computation, but instead we can actually remove everything except C's salary. And it shows that in this particular case, for example, MPC actually doesn't protect C's, the salary of C, because it can you can sort of basically reverse the whole computation, and what you're left with is essentially the output. So it shows that at least for this particular computation, the average salary of 3 people, which may or may not be an interesting application depending on what you want to use it for, you really have to consider like what is your threat model here? Is it does it make sense? Like, is it realistic that people will share their salary with each other? Meaning, are we interested in, like, is there actually something to protect here? Is there some privacy to be meaningfully preserved? There's another very interesting thing, nothing to do with privacy, but sort of to do with efficiency that this example illustrates. So notice how in both the cases where we look at what C can actually learn, the first step we do is that we undo the addition. Everybody knows that we're dividing by 3 because everybody can see that there's like 3 people who provide inputs to this computation. So both C, when it tries to see what it can learn about the inputs of A and B, and what A and B see what they can learn about the inputs of C, both of them, the first thing they will do is undo this addition. But this sort of tells us that this addition, at the very least, has no effect on privacy. It's something that everybody can just undo, so it may as well not be there. It doesn't provide us anything. So we can actually move this out, meaning that what the MPC box now does is not actually compute an average salary, it just computes a salary sum, I guess you could say. So it computes the sum of everybody's salaries and then outputs this, and now everybody can divide by the number of inputs in order to receive the average salary. The reason we want to do this now is we move this division outside the box. And if you have ever tried to implement a division algorithm on a machine that does not have division already supported in it, then you know it's a kind of complicated algorithm, and it's not super easy to implement, and in particular it's kind of expensive. And if it's expensive on hardware or on a normal computer, then guaranteed it's expensive in MPC. So especially something like divisions, if we can avoid them inside the MPC computation, then avoid them inside the MPC computation. So it's an easy optimization in this case. Not all optimizations are easy, of course, but this at the very least shows that you can sort of use this privacy idea or privacy property here to sort of infer what is actually needed there, what is not needed. The second example I wanted to go through here, the last example, are these front-run safe swaps. The function is incredibly simple here. It's simply the identity. So the MPC computation will receive a function will receive an input, a single input, and then it outputs that thing again. So in order to, like, the way you do a swap here is, well, super simple. A provides a swap as an input to an MPC computation. It means it's lying here encrypted somehow. The MPC box does, well, no computation, and then it outputs the swap. The result of the computation is the swap that A wanted to execute here. So now, why does this prevent front running? So let's consider what happens when this other party B tries to front run the swap provided by A. So B can of course see that A is now providing inputs. So just as you would do in a normal front running attack, you see that somebody is trying to execute a swap. You will try to get your own swap executed before that. So that's what B does here. That's why it shows up on the blockchain before. But importantly now, since we have input independence for our MPC, B cannot make his swap depend on A's. So yes, B can make its swap be executed before A's swap, but it will have no idea what is actually inside the swap of A. So when the MPC box like executes these swaps, yes, B swaps will be executed before A, but it cannot make it meaningfully depend on what swap A is trying to execute. So in particular, it cannot front run it, because you really need the swap you're like putting in before your target, so to speak, to be dependent on the other one. Typically, you want to like sandwich two swaps or something around the person or the swap you're trying to attack. And that's not possible here because you don't know what the other swap contains. Similarly, if you wait until the MPC box actually outputs something, then you're also like without luck here. Because yes, now you could put your swap afterwards and you would actually know what it contains in this swap, but there's no way for you to put the swap before it again, because now the computation is already done. Recall the things that are written to the blockchain here are written in like a total order. So the fact that A's swap is on here and the fact that the MPC box execute that one first means that whatever B says here is going to be executed after. It's going to show up here after the swap of A. So yes, it also cannot do anything. The question, of course, is like, do we actually need MPC to do this? Because the computation we're doing here arguably has there's no privacy to be preserved here. Even if we imagine that we do multiple swaps in like one computation, you could, instead of like receiving one, we receive like 3 or 4 or 5 or whatever, and then these are executed like in a bunch. There is still like no privacy, right? Because the function is still just the identity. So what B would learn is simply that A input a particular thing. So it learns everything about A's input. But we still need MPC here, or at least a technology that is has the same properties. So again, why not just MPC? In particular, because A needs to be able to say that I want to do this thing later without actually revealing what that thing is. Because by putting its input, by making its input, the fact of making the input commits it to the swap, and more importantly in this case, it commits the order, it fixes the ordering that these swaps are executed in without actually revealing what is inside these swaps. And this MPC with input independence allows you to do this. A second property that it gives us is that it allows us to, it allows this committing to the order to be like an atomic action essentially. So A will say, I want to do this swap, and then it doesn't have to be involved again, because now executing the actual swap is up to this MPC box, not up to the party A. And this fixes like a subtle issue where you could, for example, imagine that you'd use encryption for this, or you'd use hashing or something similar that wouldn't involve an MPC box, where you can simply refuse to later reveal your swap to so you can say, I want to do this swap, and then never actually do it. And this sort of attack, if you will, also actually prevents, or allows you to do front running, albeit in like a limited sense. Okay. So yes, the conclusion is we do actually need MPC for this, or something that has the same properties as MPC. And that was my talk. Thank you very much. We have this website, Partisia Blockchain, you can visit. You can of course ask questions, because this is a recording, but you're free to send me emails or send emails to somebody if you want to learn more about MPC, or reach out to us, I suppose. So thank you.